Some animations loop forever, and your eye never catches the jump. Others snap, and it drives you crazy. The difference isn't art, it's one line of math. By the end of this video, you'll build loops that run seamlessly forever. Let's get into it. Here's the plan. First, we'll see exactly what breaks a loop. Then the one number that fixes everything. We'll write a real loop in code, scale it to 1,000 particles, spin it, ease it, and stack loops on top of loops. 11 chapters, one idea. Follow along and you'll never ship a janky loop again. Let's start with the enemy, because you can't fix a problem you can't see. Take any looping animation and watch the single moment it restarts, the jump from the last frame back to the first. If those two frames don't match, your brain registers a tiny snap, a hiccup, a glitch. That snap is called the seam, and it's the reason so many loops feel cheap. Here's the thing, your eye is shockingly good at catching it. Even a 2 or 3 pixel difference between the last frame and the first reads as a stutter. 10 times a minute, forever. It's like a song where the loop point clicks. Once you hear it, it's all you hear. Designers spend hours nudging keyframes, trying to hide the seam by hand, and it almost never works because they're treating the symptom instead of the cause. The cause is simple. The end state and the start state are different. So for the rest of this video, we have exactly one job. Make the last frame identical to the first. Do that, and there is no seam to hide because there's nothing there. Everything else is just clever ways to guarantee it. So how do we force the last frame to equal the first? With one number, and it's math you already know. Every animation is really just a function of time. At each frame you ask, where should things be right now? The trick is to stop measuring time in frames or seconds and start measuring it as a fraction of the whole. Take the current frame, divide by the total number of frames, and call the result t. At the very first frame, t is 0. At the very last frame, t is 1. In between, t slides smoothly from 0 to 1. That's the entire idea. Now here's why it's powerful. Instead of scattering timing logic all over your code, this thing starts at frame 90. That thing ends at frame 200. You drive everything from t. Position is a function of t. Rotation is a function of t. Color, scale, opacity, all functions of t. You've compressed the whole timeline into a single dial that runs 0 to 1. And because it always ends at exactly 1, you now have a fixed target to aim at. Whatever your motion does, you just need it to come home when it hits 1. Now the single most important trick in this whole video. We need motions that automatically return to their starting value when t reaches 1. And nature already gives us the perfect tool, the sine wave. Sine is periodic. It rises, falls, and comes right back over and over, forever. Write sine of 2 pi times t. As it runs from 0 to 1, that expression completes exactly one full wave and lands precisely back where it began. Position matched, seam gone. But here's the beautiful part. You're not limited to one wave. Multiply t by 2, and you get 2 full cycles in the same span. Still perfect. Because 2 whole waves also end at the start. Multiply by 17 and you get 17 cycles, still seamless. The rule is, any whole number of cycles is guaranteed to loop. Now watch what breaks it. Multiply by 2.5. The wave gets halfway through its third cycle when t hits 1, freezes mid-swing, and slams back down to start. That's a seam, and it's the #1 reason loops fail. Someone used a fraction where they needed an integer. So burn this in. Whole cycles loop, fractional cycles snap. Integers are your safety rail. Enough theory, let's write one. Line by line. First, get t, const t equals frame, divided by duration. That's our 0 to 1 dial. Now let's move something. Say we want a dot to bob up and down. We write y equals math dot, sin of 2 pi times t. Multiply that by an amplitude to control how far it travels, and add it to the center of the screen. 3 lines. Press play, let it loop, and watch. The dot rises, falls, and returns without a single hitch because we used exactly 1 cycle of sine. Want it to bob faster? Don't touch the frame rate, Don't add timers, just multiply t by a whole number inside the sign. Times 2 bobs twice as fast, still seamless. Times 3, 3 times as fast, still seamless. Want it to move in a circle instead? Use sine for y and cosine for x with the same t, and it orbits, looping forever. That's the whole pattern. You describe motion as a function of t, you keep your cycles whole, and the loop takes care of itself. No keyframes, no guesswork, no seam. Sine is perfect for things that swing back and forth, but a lot of motion doesn't swing. It only goes one way. A progress bar filling up, a star field drifting past, a number counting higher and higher. If a value just keeps growing, it can never naturally return to its start. So how do we loop it? This is where fract saves the day. Fract, short for fractional part, does one tiny thing. It throws away everything before the decimal point and keeps only what's after. Fract of 3.7 is 0.7. Fract of 5.2 is 0.2. So take a value that grows without limit, say times 3, and wrap it in fract. As it climbs, that product climbs too. 0.5, 0.9, and then, instead of hitting 1.1, fract snaps it back to 0.1. It climbs, resets, a perfect sawtooth that loops every time. This is the secret behind scrolling backgrounds, falling rain, infinite tunnels, anything that streams endlessly. You let it grow, you wrap it in fract, and the growth folds back on itself into a seamless loop. Sine handles back and forth. Fract handles onward forever. Here's where it stops being a trick and starts being magic. Everything so far moves one thing, but the same rule scales to 1,000 things without any extra work. Picture a field of 900 particles. If they all moved identically, it would look like a machine. So we give each particle its own head start, a random seed, a number baked in when it's born. Its phase becomes fract of its seed plus t times some whole number. Because every particle has a different seed, they're all at different points in their journey at any moment. One is being born while another is fading, while another streaks across the middle. The field looks alive, organic, even chaotic. But here's the payoff. Every particle shares the same t, and t loops perfectly. So at the exact instant t returns to 0, every single particle, all 900, each on its own path, resets in perfect lockstep. Chaos on the surface, clockwork underneath. 900 independent stories, 0 seams. This is the core insight of generative motion. One shared clock, many offset phases. Master that, and you can animate crowds, swarms, star fields, and rain, all looping flawlessly from a single line of math. Let's talk about the easiest loop in existence, rotation. Think about what a circle is. You start at an angle, you go all the way around, and you end up exactly where you started. A full turn is 2 pi radians, and by definition, it closes on itself. So if you want anything to spin seamlessly, you set its angle to 2 pi times t. At td equals 0, the angle is 0. At td equals 1, the angle is 2 pi, which visually is the same as 0. The spinner has made one complete revolution and returned to its exact starting pose. No seam is even possible because a full rotation is self-closing. Want it to spin faster? 2 pi times 2 times t gives you 2 full turns. Times 5 gives 5 turns. As long as it's a whole number of turns, it lands home. This is why hypnotic spirals, loading rings, and vortex backgrounds feel like they could run forever, because mathematically they can. Rotation is the one case where the loop is basically free. Set the angle from t, keep the turns whole, and you're done. It's the perfect starter loop, and it never fails. Now a mistake that catches almost everyone, including pros. So far, our motion has been mathematically smooth, but sometimes it feels robotic, perfectly even, no life. So we reach for easing, slow in, slow out, that natural acceleration in deceleration that makes motion feel real. Here's the trap. A loop doesn't just need to match position at the ends, it needs to match velocity, speed too. Imagine a dot that eases from left to right. It starts slow, speeds up, and screeches to a halt on the right. Now the loop restarts, and suddenly it's back on the left, moving slow again. Even though the positions might line up, the speed jumped from 0 to fast in one frame. Your eye reads that as a stutter, a little kick every single loop. So what's safe? Symmetric easings, ease in out, where the start and end both move at the same gentle speed, matches velocity at the seam. Anything built on sine is naturally safe, because sine's slope at the start of a cycle equals its slope at the end. The rule expands. For a seamless loop, match position and velocity at the boundary. Do that and you can ease all you want. The loop stays invisible. Let's put everything together in the most satisfying demo in motion design. The pendulum wave. Line up 15 pendulums in a row. We give the first one 18 full swings per loop, the next 19, the next 20. Each pendulum gets the next consecutive whole number of swings, all the way up to 32. Now, why does this work? Because every single count is an integer. Every pendulum completes a whole number of swings exactly when it reaches 1. That's our rule from Chapter 3, applied 15 times at once. Watch what happens. At the start, they're all lined up, released together. Immediately, they begin to drift apart because they're swinging at different rates. Within seconds, you get gorgeous traveling waves, then apparent chaos, then snaking patterns that look completely random. But it's not random. It's 15 integer cycles quietly counting down. And then, at the exact loop point, every pendulum finishes its whole number of swings at the same instant and snaps back into a single straight line. Perfect unison out of total chaos. Different speeds, same finish line. It's mesmerizing, it's hypnotic, and it's nothing but integer cycles sharing one clock. By now you've got the rule. One shared T, whole cycles, wrap growth with fract. The final superpower is that these loops compose. You can stack as many as you like, and they all still loop together. Picture a grid of tiles. Give it a slow brightness pulse, 2 cycles over the loop. Layer on a fast shimmer, say 11 cycles. Add a rotating hue that turns 3 full times. Throw in a wave that ripples across 5 times. Each layer uses its own whole number of cycles, but every one of them shares the exact same T. So here's the guarantee. Since each layer independently returns home at T equals 1, the combined result, no matter how many layers you stack, also returns home at T equals 1. The motion can look impossibly intricate, almost alive, with rhythms crossing and interfering in ways you could never keyframe by hand. Yet it loops flawlessly because underneath the complexity, every ingredient is a whole number. This is how those endlessly mesmerizing backgrounds are built, not by animating every detail, but by layering a handful of simple integer loops on one shared clock and letting the math do the rest. All right, let's lock it in. 3 rules, and every seamless loop you'll ever make comes down to these. Rule 1, map time to T, current frame divided by total frames, so your whole animation runs on one number from 0 to 1. Rule 2, drive every motion with a whole number of cycles, sine, cosine, rotation, whatever swings or spins, multiply T by an integer, never a fraction, so it lands home at the end. Rule 3, anything that only grows, scrolls, counters, drifting fields, wrap it in fract so it folds back and resets clean. And the bonus rule from Chapter 8, match velocity, not just position, so your easing doesn't betray you at the seam. Follow these, and something powerful happens. You're no longer hoping your loop is seamless and eyeballing it frame by frame. You've made it seamless by construction. The last frame is mathematically forced to equal the first. There is no seam to find, no glitch to chase, because it literally cannot exist. That's the difference between guessing and knowing. Pin these 3 rules above your desk. So here's the whole secret in 3 lines. 1. Map time to T, frame over duration, 0 to 1. 2. Drive every motion with a whole number of cycles. 3. Wrap anything that grows with fract so it resets clean. Do that, and the last frame becomes the first. The loop never ends. That's the trick behind every seamless loop you've ever stared at. If this made motion click for you, Hit like, subscribe, and tell me what to build next. I'm 9. See you in the next one.